All right, guys, today we're going to look at exponential functions and their graphs. Like y equals a to the x, where a is greater than 0, but it cannot be 1. These exponential growth and decay functions we did in Algebra 2, so they should seem pretty familiar. So to graph these, our first number, we've got the base is a number and the exponent is a variable. So the first equation is f of x equals 2 to the power of x. So 2 is the base, and then we have, of course, our variable x. To graph this, we're going to make table values. And with our table values, I always want to see a table with at least 3 or 4 points on it. So let's make a table. Typically, the points I use are -2, -1, 0, 1, 2. Okay, I know that's 5 points, but it's better to have more points than less points. So I'm going to start with that. So 2 to the -2 is 1 over 2 to the 2nd, which is 1/4. -1 is 2 to the -1st, which is 1/2. 2 to the 0 is 1. 2 to the 1 is 2, and 2 to the 2nd is 4. Okay, so we're going to plot those points. -2, 1/4, -1, 1/2, 0, 1, 1, 2, and 2, 4. Okay, this is an exponential growth function. There we go. I could get more points, but we don't need them. That's those 5 is plenty. Now with these, we're going to look at 2 things. We're going to identify and graph the asymptote. The asymptote here is the line y equals 0, and it is the line that the graph gets really, really close to but never actually touches. So we're going to identify the asymptote, and we're also going to identify the domain and the range. The domain, we know how to find. Left and right, the graph goes from -infinity to infinity. And then the range, low to high, the lowest is 0, and the highest is infinity. 0 is the asymptote, so it has to get a parenthesis because the graph doesn't actually touch it. So we leave it as a parenthesis. Okay, number 2. Number 2, if you remember these from Algebra 2, if you have an addition or subtraction in the exponent position, that is the movement left or right. In this case, it's x plus 2. It's the opposite of that, so -2. So the whole graph that we just drew is going to shift to the left 2 units. Okay, we're going to see that by making a table. -2, -1, 0, 1, 2. And we're going to plug those in. If I plug in -2 plus 2 is 0. 2 to the 0 is 1. -1 plus 2 is 1. 2 to the 1st is 2. 0 is 2 to the 2nd is 4. 1 would be 2 to the 3rd, which is 8. And then 2 would be 16. That's kind of high. We don't have to graph that one. So -2, 1. -1, 2. 1 is, or 0 is 4. 5, 6, 7, 2, 1 is 8. So this graph, the whole graph shifted. If we look at the graph we did a moment ago, the whole graph shifted to the left 2 units because of this 2. Okay, the asymptote, the line that the graph is going to get really close to but not touch. We've done those before. Y equals 0. The domain is -infinity to infinity, and the range is 0 to infinity. Okay, graphing exponential functions. Next, we're going to graph with the natural number e. E is the natural number, and because this e, which is 2.718, is not, they're not whole numbers, we can use our calculator. So if we were having this one, this would be a calculator portion of our test if we had this one on there. So I'm still going to use -2, -1, 0, 1, 2. So grab your calculator, plug it in into the y equals equation. Now the e is along the left-hand side. It's under the ln key. So go second ln, and then when you put that in, it automatically gives you an exponent. All of the e's are exponential equations. So it'll do e to the power of, and then you just do e to the power of x. Okay, so we plug that in, and I will give you the points On these, I rounded to the hundredth. So -2 is 0.14, -1 is 0.37, 0 is 1, 1 is 2.718, and that is the natural number right there, e to the first. E to the second is 7.39. Okay, let's graph it. -2 is barely above the axis. -1 is 0.3, a little bit higher. 0 is 1. 1 is 2.7, and 2 is 7.39. Right about there. So this graph again has a horizontal asymptote at 0. Horizontal asymptote at y equals 0. And then the domain, -infinity to infinity. It keeps going left and keeps going right. Range is again 0 to infinity. Now our next one, we're going to move up or down. But those first three, and the most common horizontal asymptote is that y equals 0. All right. Next is e to the -x plus 2. When you have a negative in the exponent position, it flips the graph. Okay, so because of the negative in the exponent position, this is an exponential decay function. So instead of starting low and going up high, it starts high and then comes down low. So I'm going to make my table. -2, -1, 0, 1, 2. And plug it in the calculator. Make sure when you put it in the calculator, you move over so that your cursor hops back down and do the +2. Now this +2, it's going to take our graph and shift it up 2 units. It shifts it up 2 units. -2 is approximately 9.39. -1 is 4.72. 0 is 3. 1 is 2.37. 2 is 2.14. All right, so -2 is 9.3, which this graph only goes up to 10, so it's right about there. -1 is 4.7. 0 is 3. All right, I'm back. 1 is 2.37. 2 is 2.14. Okay, so exponential decay, it starts up high and then it comes down low and then it flattens out. So in this one, the asymptote, because of that +2, the asymptote shifts up 2 units. So my asymptote here is y equals 2. So my domain is -infinity to infinity, and then my range is 2. And then the range is going to be 2 to infinity. Okay, so that's it for the graphs. Now we're going to move on to some compound interest. You did compound interest in Algebra 2. A equals P times 1 plus R over N to the NT. Now that formula is true when it compounds monthly, daily, yearly, whatever. Continuous compounding is PERT. A equals PE to the power of RT. PERT. So here we're going to just plug them in. You guys should have seen these formulas and used these formulas before, so I'm not going to spend a lot of time on those. So number 5 here. So we have A, which we don't know. So A equals 6,000 times 1 plus our interest rate is 7.5%, so 0.075, divided by N is the number of times it compounds per year, so that's going to be our 12, to the power of 12 again, times the number of years, 12 times 3. Now make sure when you put this in, you use your parentheses and you use your fraction key correctly, so it'll come out right. So if you get some crazy number, it's not going to make sense. If we're investing for 12 years, we're not going to end up with like $1 million or, $500,000 or something. So plug that in. And this first one, I just plugged it in, and it is $7,508.67. With the money, we always round to the nearest penny. Now that the more you compound, the more money you make. So in this one, we're compounding monthly, so 12 times. For example, B, we're compounding less. We're compounding annually, so that's only 1 time per year. So same formula, 6,000, 1 plus 0.075 divided by 1, which we don't really need that 1, but I'm just showing you there for a placeholder, to the power of 1 times 3. So plug that in. So the first equation gives us 7,500. This one should be less, and it is. It's $7,453.78. Okay, now this last one here is continuously. So continuously we use PERT. PERT is A equals P, 6,000. Move this up a little bit. E is the E button in the calculator, excuse me, to the power of R, 0.075, times the number of years, PERT. A equals PE to the power of RT. Now, compounding continuously is like every second of every minute of every hour of every day. So that's always going to be the highest if you have the same P and the same rate and the same number of years. So that one comes out $7,513.94. So that, even though it's not a lot more, it's always going to be at least a little bit more than the compounding monthly.